Okay, let's take a look at the 4-7 notes for Precalculus 2. So you can open up to your note packets. Basically, we're going to have to do a little bit of algebra review, a little bit of pre-calc review, pre-calc 1, just to get started here, before we can actually get into inverse trig functions. So right off the bat, just remember, if we had let's say we had a graph of a function like this, we would use in order to determine whether this is a function or not, we would draw lines like this, and the line could only intersect the curve in one point. Okay, just to recall, this was of course called our vertical line test. So we use a vertical line test in order to determine if something's a function. So if you look really closely at our sine graph over here, you can see that if we drew a vertical line through anywhere on the sine graph, we would of course only intersect at one point, or the cosine graph, or our tangent graph. No matter what we do, we intersect in only one point. So therefore, we have a function, right? So in Precalc 1, you actually learned about inverse relations. That was sort of a big topic that you had to know about in there. So what was the deal with inverse relations? So just as a sort of a review, so if you had, let's say, y is equal to 2x plus 5, right? So you learned in order to find the inverse of that function, you had to swap out the x and y variables. So you would get x is equal to 2y plus 5. And then in order to find the actual inverse function, we had to solve for y. So what would we do? We would subtract the 5 over, then we would divide by 2, and we would essentially get this as our inverse relation. But both of these are linear, and linear functions that are not vertical are going to be basically functions. So we would say, hey, we can change the symbolism to f inverse of x is x minus 5 over 2. Okay, so that was the whole process of finding inverses. It's essentially swapping variables. So returning to our lesson here, the more important element of this is whether the inverse relation is a function itself. So over here, we determine both of these are linear, so it's a function itself. But it's not always that easy. So it says graphically, this can be confirmed by using the horizontal line test. Okay, the horizontal line test was used to determine if a function's inverse is also a function. Okay, we also had a name for this. If the function's inverse was also a function, we would call it 1-to-1. Okay, so just as a sort of expanding this to, let's say, trig. So if you look at the graphs along this line right here, we have sine, cosine, and tangent. If we try using the horizontal line test, which is all of these sort of magenta lines that you see right here, you can see that these horizontal lines, no matter what graph you throw them through or draw them through, you are going to intersect in more than one point. So what does this tell us? This tells us that the inverses of each one of these functions is not a function. Okay, that can be kind of simple to understand just because the inverse of the function is just going to turn this on a different axis, which I'll show you in a second. But withstanding of that, the idea is that when you don't have a function, it's not very useful. So basically, mathematicians decided to make inverse trig functions more useful by making them functions. So how did they do that? So if you look here, essentially what they did was they took the original, this is the original sine function, and they cut it off. They changed the domain of the function so that it only goes from negative pi over 2 to pi over 2, which is from here to here, right? Here to here. So when you actually swap the x and y coordinates, you actually end up with this graph. So this is the graph of y equals sine inverse of x, or in other words, inverse sine. Now note, this is sometimes also called arc sine, just like that. So just in case that comes up if you're looking online or something. It's also called arcsine. But what this does is it allows us to look at a graph and make it usable. So note, if the actual sine graph just keeps on going on forever this way, the inverse sine graph. But we know that that is not going to be useful because it won't be a function. So what we've done is we've essentially changed the result by limiting how high and low it can go on the graph. So since the domain was altered here, when we switched to the variables, that means the range was altered. So this green circle here, this is going to be the most important thing about this graph. You're not going to be asked to graph an inverse sine, but you're going to be asked to evaluate inverse sine functions at certain values. So the key is going to be that range that you see right there. Now the same can be said for the other graphs. So instead of what they did for cosine is they limited it from 0 to pi, our domain. So therefore, when you switch it so that it becomes x and y switch places, you end up with this graph, which now has a range of 0 to pi. Again, this is going to be the key concept that we're going to have to manage as we go through the problems, and I'll show you a summary of that later. But this right here is going to be our graph of cosine inverse. Again, it would go on forever, this way and this way, but we're cutting it off just to there in order to create a function that is usable for us. Okay, lastly, the tangent graph, which basically looks like this, right? Okay, it goes forever that way. So what they do is they logically cut it off between the asymptotes. So in a tangent graph, remember the asymptotes are between negative pi over 2 and pi over 2, the primary ones that we start with, and we use that when we're graphing them, if you recall. So what they do is when you swap the variables, you end up with this graph over here, and the domain becomes the range, and these are going to be the key values. So this becomes useful because the vertical line test basically confirms that it's going to be a function. All right, so we have a nice summary of our inverse trig functions. And note, yes, you see it's arcsine, arccosine, arctangent. I didn't mention that arc is basically the word that's used in order to mimic the inverse function, or it's another word for it. So you won't see that a lot in your textbook, but in case you look online. So the key column here is going to be the ranges of these functions. These ranges are going to help us work with these problems. You want to memorize these ranges. The good news is that sine and tangent have a similar range, and cosine is basically the other version of it. So let me just read here so you understand what we're actually doing when we're finding an inverse. It says the first thing you realize when finding inverse trig function is that it's simply the reverse process of finding a typical trig function value. Normally, you are asked to find the trig function value of some angle, let's say the sine of pi over 4, and you would quickly obtain root 2 over 2. Now, you will be asked for the sine inverse of root 2 over 2. So note, the answer that we found is now going to be what's going to be evaluated. So this is basically asking you to find all angles in which the sine evaluates to root 2 over 2. This should lead you back to the result of pi over 4. Okay, so all it is the reverse process of finding a very typical trig evaluation. So the sine of pi over 4 is root 2 over 2. So therefore the sine inverse of root 2 over 2 gets us back to pi over 4. This can be very simple, but it also, students seem to struggle a little bit with it just because, you have to work backwards. And anytime you work backwards, it can be a little bit of a difficult, thing for the brain. So that's what we're going to concentrate on as we go through the process to try to figure this out. Okay, so let's look at some examples. So it says for number 1, we are looking for the sine inverse of -1/2. Okay, so if we look at our range for sine of inverse of x, it only occurs between negative pi over 2 and pi over 2. So if we look at these values, we know that pi over 2 is located over here, correct? But we also know negative pi over 2 is located down here. So therefore, our answers can only occur from here to here on our unit circle, which means we effectively eliminate these two quadrants as possible answers for our problem. This is the key first step that you always want to make in any inverse trig function evaluation. So let's talk about what this function here actually means. So if we're doing the sine inverse of -1/2, they want to know the angle of theta, where the sine of theta is going to be -1/2 on -π/2 to π/2. Okay, so how do we find that? Well, we know that the sine of theta is always the y coordinate. So if, just as a review, remember that, throw this over here somewhere. We know that the sine of theta is always y, the cosine of theta is always x, and the tangent of theta is always y over x in the unit circle. So we'll leave that there. Okay, so we're looking for when the y coordinate is basically -1/2. So just generally, we don't have to worry about the negative for now. We can just say, okay, well, when is the y coordinate 1/2? Well, it should be logical to you that if the y coordinate is 1/2, the x coordinate has to be √3/2. Okay, and where does this occur? This occurs at π/6. So if we look at our picture, basically we have two options for where π/6 could fall. We could go up π/6, or we could go rotate backwards -π/6. Okay, so the question is which one of these is going to create a negative answer? Well, this should be fairly straightforward if we do all students take calculus. Sine is positive in quadrant 1, it creates a positive result, and it is negative in quadrant 4, where the c is. So therefore, if we have a -1/2 as a result, that we must be talking about the fourth quadrant, which means the answer to this problem is actually going to be our -π/6. Now, I know you're not used to writing -π/6, so hypothetically, I'm perfectly fine with you writing the alternative to that, which is actually, I'll write or 11π/6. You can write either one of these. I don't really care which one you write. In the book, though, you're going to find this much more often for the inverse sections. Okay, so moving on. So let's see if we can sort of get the concept here. So cosine inverse of √3/2, positive. So if you look up here, the cosine inverse has a range of 0 to pi. So what are we looking for? We're looking for the value of theta, where the cosine of theta is going to be √3/2 on 0 to pi. So this has changed a little bit. So if you look at 0 to pi, that now is not quadrant 1 and 4 anymore. That is actually from 0 to pi, which encompasses the first two quadrants. So therefore, the answer to this problem cannot be in quadrant 3 or 4. So all of our work is going to concentrate on the quadrant 1 and 2. Okay, so if you're looking at cosine, we know that the cosine of theta is actually equal to the x-coordinate. So what are we looking for? We're looking for when √3/2 is the x-coordinate. Well, we know that that occurs when the y-coordinate is 1/2. And where does that occur? Well, just as we did in the previous problem, that occurs at, again, π/6. So the question is, what are the different π/6 rotations in this scenario? Well, in the first quadrant, it's just π/6. But the π/6 rotation in the second quadrant is actually 5π/6. Okay, so therefore, the solution to our problem is going to be either π/6 or 5π/6. So if you look at our result here, we have a positive result. So if we look at our all students take calculus, you can clearly see that cosine is positive in quadrant 1 and negative in quadrant 2. So since we have a positive root 3 over 2, that means our answer has to be the one in quadrant 1, which means the result is simply going to be pi over 6. Okay, looking at number 3, we basically have the other trig function. So the tangent inverse of -1. Okay, so this is going to take a little bit of remembering. So remember, the tangent inverse is equal to y over x. So if you're at y over x, we have to mentally remember, well, how do we get the tangent of theta equal to y over x? Well, for that to be essentially 1. Well, the only way that works is if y and x are the same thing, and the only coordinate that actually works for is when you have root 2 over 2, root 2 over 2, okay, which we know occurs at pi over 4. So basically in this setting, we're considering pi over 4 to be the family that we're concentrating on. But again, if we go to tangent inverse, in our setup, this actually only occurs, again, from negative pi over 2 to pi over 2. So where are we? We're back in the first and fourth quadrants and eliminating our second and third quadrants. So what are the possible rotations of pi over 4 in these quadrants? Well, we could go pi over 4 this way, or we could go negative pi over 4 this way. So the question is which one of these is going to create a negative result? Because what are we looking for? We're looking for a theta where the tangent of theta is equal to -1 on negative pi over 2 to pi over 2. So where does this all occur? Well, this occurs negatively, clearly at the fourth quadrant, because everything is positive in the first quadrant. And again, just to verify, this is the C, so tangent is negative. So we now know that the result of our problem is going to be negative pi over 4. Okay, just as a general summary here, in case this is not easy for you, if you look at number 1, 2, and 3, the process is very streamlined. Essentially what you do is, in the beginning, you rule out 2 quadrants using the ranges up here, right? So you rule out 2 quadrants based on which function you have. Then you're only left with 2. So you look at whatever, obviously you have to find what radian family each one of these values is going to result in using the formulas up here. But generally, it's either going to be positive and negative. So out of the 2 remaining quadrants, you'll be able to quickly find which quadrant it has to be in. Once you're there, then you can determine the rotation and you are good to go. Okay, so let's look at some other examples here, so a couple more. So look at number 4. We're doing the cosine inverse of negative root 2 over 2. So just as a summary again, what is that? So we're looking for basically when the cosine of theta is equal to negative root 2 over 2. And remember, cosine is from 0 to pi, so on 0 to pi. Okay, so again, what are we dealing with? First and second quadrant, so we can eliminate these. Now, that means that we're dealing with one of 2 rotations. It's going to be basically this one or this one, right? Okay, and which quadrant they're in. So let's determine which values are going to be that. So we're looking at cosine. So when is the x coordinate root 2 over 2? When the y coordinate's root 2 over 2, which happens at the pi over 4 family, right? So that means this is going to be pi over 4, and then the other rotation is going to be the pi over 4 rotation in the second quadrant, which is right before 4 pi over 4, which is 3 pi over 4. Okay, one of these is the answer, but this should be very clear because we have a negative root 2 over 2. The negative is only going to occur in this quadrant right here. So therefore, our answer must be 3 pi over 4. Okay, so number 5. Anytime we get to a tangent inverse, just like number 3, things can get a little bit tricky because we're dealing with y over x. So essentially, we have to do some mental division. So recall, we did that mental division here because we said well, how do we get 1 with y over x? It's if you divide something by itself. Now, we have root 3 over 3 as this result. Okay, so I'm going to move over here and do a little bit of fancy math over here, right? So root 3 over 3 is not one of our fancy coordinates. It can't be. It's basically as a result of division. So we have to be very smart about where this value actually came from. So when this is as a result of rationalizing the denominator. So essentially what happened is you multiplied some fraction times root 3 over root 3 in order to get root 3 over 3. So what was that fraction? Well, that fraction was actually 1 over root 3. Okay, there's not a lot of these, so it's just about becoming comfortable with where root 3 over 3 came from. So basically what you have to figure out is, how do I get y over x the same as 1 over root 3, but coming from one of our special families? Well, clearly, if there's a root 3 involved, then it's got to be pi over 3 or pi over 6. So what are we looking at? Well, let's just, in this scenario, if we're creative about this, then we can say, okay, well, isn't this also the same as this? Okay, so if you remember, we would have crossed out these 2's and ended up back at 1 over root 3 when we did a little bit of our fancy math, algebra, and computation. So if we look at this, we're saying, when is the x-coordinate root 3 over 2, and when is the y-coordinate 1/2? Well, let's look at it. Root 3 over 2 comma 1/2 clearly occurs at pi over 6. So I know there's a lot of extra work over here, right? But basically, this was used in order to identify that we're in the pi over 6 family for this problem. So just to be clear again, we're looking for theta, where tangent of theta is root 3 over 3, but we're going to be on negative pi over 2 to pi over 2. And again, where am I getting that from? That's going to be memorization from you, but that's going to be here. Okay. So where are we? Well, we're actually in quadrants 1 and 4, so we're eliminating 2 and 3. So the question is do we want to rotate up to pi over 6 or down to negative pi over 6? Well, clearly this is a positive answer, which is going to eliminate our negative rotation into the 4th quadrant. So we're going to be at an answer of pi over 6. Okay, so last one here, cosine inverse of 0. So we're looking at where 0 is equal to the cosine of theta on 0 to pi. Okay, so again, what are we eliminating? We're eliminating these two quadrants. So we're looking for when essentially cosine, remember, is the x-coordinate. So we're looking for when the x-coordinate is 0. Okay, that's kind of weird, but if you realize that that does not occur at any of our popular families, that's actually one of our popular angles, remember, or popular coordinates on our unit circle. That actually occurs at 0, 1, believe it or not. So if you look, the x-coordinate is 0, it occurs at 0, 1. So in this standpoint, we don't have to go through as big a process. We can just say right away that this clearly results at a rotation of pi over 2. Okay, so just as a summary of these problems, it's extremely important that you get this down in terms of practice, because as we move now to scenarios that are more involved, you obviously need to know the basic skill of what's up here. So moving on, we're going to talk about the concept of composition. So in Algebra and Precalc 1, you learned about this type of function notation. We would say f of g of x. So when we do f of g of x, basically the idea is we always work inside out. So we would evaluate g of x, and then whatever value we would get for that, we would then plug into f, essentially, right? So if you look at what's going on up here, basically what they're doing is they're composing a function and its inverse. Okay, so if you look at this, it says if you take f of the f inverse of x, you should end up back at the value of x. Well, that makes a lot of sense. If you plug something into its inverse and then take the result and plug it back into a function, you're going to end up with the original result. But that can only occur if all of the domain requirements are actually set. So the domain requirements are here, but this can be very confusing by just looking at the gray box, right? So the best way to do it is to really understand an example. So we're going to do that just to make sure that you understand when these formulas work and when they don't. So let's start here. It says, evaluating compositions can be a bit tricky due to restrictions presented above. To make this clear, let's look at two compositions. So we're going to start with this one, and then we'll move on to the other one after it, and hopefully that'll help you understand what is going on. So it says, recall that we evaluate compositions, we do inside out, as discussed. We can quickly find that the cosine of pi over 4 is what? Okay, so quickly meaning, ready? So we know that we have our unit circle. We know that pi over 4 creates a coordinate of root 2 over 2, root 2 over 2. Okay, cosine, the cosine of theta is always the x coordinate, so we're looking here. And if we're talking about a positive result for that, that means that we are going to end up with essentially root 2 over 2 as our result. And just to be clear with that, obviously pi over 4 is in this quadrant, so if we do all students take calculus, we have a positive result in that quadrant. Okay, so moving over here. So what can we do? We can now take root 2 over 2 and replace the cosine of pi over 4 in this setup. So we're basically here, becomes root 2 over 2, which means we end up with this. Okay, so what do we do now? So now we want to find the cosine inverse of root 2 over 2. So remember, what are we doing? We're back to the problems on the previous page. So what do? We have our unit circle. So the cosine inverse of root 2 over 2, cosine is limited to 0 to pi. So we eliminate these two quadrants. So therefore, we're dealing with rotations that are either in the first or the second quadrant. Now, root 2 over 2 as an x-coordinate only occurs at pi over 4. So basically, we would be dealing with a rotation of pi over 4 or, in this case, 3 pi over 4. Because it's a positive root 2 over 2, we end up with pi over 4 as our answer. So therefore, we end up with the following statement. The cosine inverse of the cosine of pi over 4 is pi over 4. So looking back. So if we look at this right here, you'll see that this is the exact formula, if you look at these two things here, that we had before. If we replace this with x and this with x, basically that's what we get. So what the book is telling you, or what it's trying to explain to you, is that if you use this formula, you can actually do this faster. But here's the problem. This only is true on the following interval, 0 to pi. So clearly, pi over 4 in this setup for what you're doing, so in this case, our pi over 4 that's listed in our original problem here, that is between 0 to pi. Therefore, we know that this formula is going to work. But what if we decided to take a value for x right here that is not from 0 to pi? So look at this guy here. So 5 pi over 4 is actually, from our setup, in quadrant 3. Okay, so it is not from 0 to pi in our setup. So what happens then? So how do we manage that in terms of our setup for what we do? So what it's telling you is that you cannot use this formula right here now in order to use this problem because it doesn't fit on our range of values. So let's verify that to make sure it's true. So first things first, let's find the cosine of 5 pi over 4. Well, we know that the reference angle for 5 pi over 4 is just pi over 4. So we know that we're dealing with root 2 over 2, root 2 over 2. The question is, where are we in what quadrant? Well, we determined that's in quadrant 3. So if we do all students take calculus, we know that the cosine is actually negative in quadrant 3, which means that if we take the cosine, which we know is the x coordinate, so remember cosine of theta is x, then we're taking the negative version of root 2 over 2 as our result. So if that's negative root 2 over 2, then we go, all right, well, let's put this over here. Negative root 2 over 2. We now have to find the cosine inverse of negative root 2 over 2. Now, if you look at from number 4, we already did that. The cosine inverse of negative root 2 over 2 actually ended up being 3 pi over 4. So if we go back to this, we get 3 pi over 4 as a result. So take a peek. If I do a summary without all the work, it says the cosine inverse of the cosine of 5 pi over 4 is actually 3 pi over 4. So again, the formula cosine inverse of the cosine of x is not equal to x because 5 pi over 4 is not in the interval 0 to pi. So what is my sort of summary of this type of setup whenever we're doing them? I personally don't love these formulas here. Why? Because students get hopelessly confused with the proper intervals and where they are. So what I always say to students is, just if you're going to do one of these problems, just do the problem inside out. Find cosine of 5 pi over 4, then find the cosine of the result. If you do that, you're just going to get an answer. As long as you can do both things, then you'll be fine, and you don't have to worry about memorizing theorems that you could end up getting wrong in the whole, gist of things. So I always recommend just doing the math out like we did in this one down here, and then you won't usually run into any issues. Okay, so let's do examples of composition. So again, what are we doing? We're composing a function with its inverse. Okay, so what was my suggestion? My suggestion was, if you don't want to deal with all of these properties up here, I know it's a little messy now, but if you don't want to deal with all these properties and remembering the ranges, you can simply just evaluate this inside out. So for example, if we want to find the cosine inverse of negative 1/2, we're looking for when cosine of theta is equal to negative 1/2 on 0 to pi. Okay, so what are we doing? We are eliminating these two quadrants, and we are only in these two up here. Okay, so again, we're basically looking for rotations in those quadrants. So 1/2, well, cosine is the x-coordinate, of course. So we're dealing with a family of radian values that starts with 1/2, which means it has to end with root 3 over 2. We know this occurs at pi over 3, which means our rotations will be at pi over 3, or the equivalent family pi over 3 in this quadrant, which is 2 pi over 3. Okay, so the key now is, which one is it? Well, because the original 1/2 is negative, that means we have to be in the second quadrant because all rotations are positive in the first quadrant, which means we know that this is 2 pi over 3, which means we can replace that in the original problem with 2 pi over 3. Okay, by now you guys should be experts at evaluating regular trig functions. We talked about that, before the break, making sure that you can seamlessly do this. So again, this is what we're going to do. Essentially, if we're evaluating 2 pi over 3, we're evaluating the pi over 3 reference angle. So we have our unit circle. 2 pi over 3 is in the second quadrant, as we've already said, right? Okay, so we're evaluating the pi over 3 reference angle. So back to here, right? We're looking at this and going, okay, well, pi over 3 has this coordinate, and cosine is x, so we want 1/2. But because we're in the quadrant with s, cosine is negative, so we want negative 1/2. So negative 1/2 would be the answer to the problem. It is, and worth noting that if you look here, we did get the same result for both of these. Why? Because this evaluates, the rule only works from -1 to 1. So if you look over here, if you look at this one right here, this only works from -1 to 1. Therefore, because -1/2 was from -1 to 1, we're going to get the same result. So again, I don't see the benefit in memorizing that. That's just my personal opinion. That's a lot of things to memorize. Instead, just doing this process, going through and figuring out what it is, and you're going to get the result as is. Okay, so for number 8, we have a little bit different setup, only because you'll notice that we don't have the typical family of radians here. We have just pi. So, but again, what do we want to do? We want to evaluate inside and out. So if we want to find the sine of pi, we need to go to pi. So if we're looking at the unit circle, pi is located over here at the coordinate -1, 0. So what is the sine? It is the y coordinate at pi, which is 0. So what can we do now? We can replace this entire value with just 0. So what is this value? Well, if we realize that this right here is a ratio, okay, this is not an angle. Over here is an angle or a rotation. So we want to know the sine inverse of a ratio that creates 0 as a result. So what does that look like? So we want to know when the sine of theta is equal to 0 on -pi/2 to pi/2. Okay, so what does that eliminate? That eliminates this one and this one. So we're only going to be in this range of values here. So you're going, okay, so when is the sine of theta 0? Well, that is when the y-coordinate in this case is going to be 0. So you look at these coordinates, look at them. So 0, 1, 1, 0, 0, -1, right? So when is the y-coordinate 0? It seems like it's only here. But what is the actual rotation at this value? Well, a lot of you might say 2 pi. That is true. That's a full rotation of 2 pi. But when we evaluate, we only evaluate from 0 including to 2 pi not including. So that means the rotation here is actually just 0 degrees. So that means the answer to the problem is 0, the angle 0. Okay, this is where this problem is actually quite confusing because of these angle ratios, because students will look at a 0 and immediately think it's just an angle. Sometimes it's a ratio, sometimes of an angle, because obviously you can get a ratio of 0/1, and that's not an angle. So just realize that as we go. So the answer to this is that. So note, the sine inverse of the sine of pi is actually equal to 0. So note that these do not match when you actually do the math. Okay, so let's wrap up with the following two problems, 9 and 10. Just realize that these problems are different and will require a different process in order to solve. Why is that? There's two main things going on here. If you look at the two functions here, they do not match, as opposed to when we look at number 8 here, they do match. Number 7, they do match. Again, they don't match, and you can look at 10.2 here and see the functions don't match. What else? Well, in the problems that we did before, -1/2 pi and 7 and 8, the values that are the ratios and or the angles are very familiar values, whereas here 3/4 and -1/4 are not. This is a good way to identify these types of problems in this setting. So just to get started with the problem and the different method is, again, what are we doing? We're working inside out. So where does tangent inverse exist? It exists from -pi/2 to pi/2, which means that we are eliminating these two quadrants and we're only from here to here. Now, besides that, we have a positive 3/4. If it's positive, it cannot occur in quadrant 4. It must occur in the first quadrant. So if we're in the first quadrant, we can actually create a right triangle with an angle theta, just as such. It's called a reference triangle with a reference angle. We also can label this triangle because we were given that the tangent is inverses of 3 over 4. Remember, tangent is opposite over adjacent. So we're going to go to our triangle and to theta, and we're going to go opposite, and we're going to put our 3, and we're going to go adjacent and put our 4. With this, we obviously have the hypotenuse blank. Now, most of you know by now that this is a 3, 4, 5 triangle, but if you wanted to, you could obviously do, x squared is equal to 3 squared plus 4 squared, get x squared is equal to a sum of 25, and x is plus or minus 5. Okay, so we basically have that. So what's interesting about this is that the tangent inverse of 3/4 is essentially theta. So this is actually equal to the sine of theta. And if you look at our triangle that we just made, we can find the sine of theta. The sine of theta is opposite over hypotenuse, which is 3 over 5, which means the answer to our problem is 3/5. Okay, so moving on to 10, we got tangent of the cosine inverse of -1/4. This is going to be a little different. Let's just see how it goes. So remember the cosine inverse, we want to do that first. That exists 0 to pi. So we are eliminating these bottom two quadrants, which means we only exist from 0 to pi. Because this is a -1/4, we must be in the second quadrant. We can make a triangle. Again, we're going to put a reference angle of theta in it. So, what is cosine? Cosine is adjacent over hypotenuse. So let's label that. Well, the hypotenuse has to be positive, so that's got to be +4, which means the adjacent has to be -1. We are just missing the opposite, essentially. So what do? Pythagorean theorem. 4 squared is equal to -1 squared plus, let's just say, x squared. If we do the math, we're going to get 16 is equal to 1 plus x squared. X squared is 15. X is equal to plus or minus √15. Okay, so which one is it? Well, we're going up. So that means this right here has to be positive √15. Okay, once we get that value, then we're taking the tangent. We replace cosine of inverse of -1/4 with theta. So the tangent of theta is going to be opposite over adjacent. So that is √15 over -1, which is equal to -√15. So clearly these problems are much different. I kind of like them just because they are kind of logic problems. There's not a lot of memorization involved with this other than knowing where these functions exist at. You just draw a triangle and get the results.